please make sure you've already done the guided reading notes so you kind of have an overview of what we're going to be looking at. It'll make things a little bit easier if you're already familiar with the vocabulary. So learning targets today is to be able to use a probability distribution, which you should already pretty much be familiar with back from Chapter 5, calculating the mean and standard deviation of a random variable, and being able to interpret the mean and standard deviation of a random variable. So as you can see, a random variable takes numerical values. It's a quantitative variable that describes the outcome of some chance process. And usually we use a capital letter to represent a random variable, for instance, the letter x, because we use that a lot in math. The probability distribution of a random variable gives its possible outcomes and their probabilities. Remember this from Chapter 5. It's the sample space, all the possible outcomes, and their probabilities. The section talks about two different kinds of random variables. One is a discrete random variable. A discrete random variable takes discrete values. The probability can be represented by a probability histogram, where the height of each bar represents the probability of an outcome. A continuous random variable is where the variable takes all values in a certain interval of numbers. The probability distribution is described by a density curve, where the probability of any event is the area under the curve. So the difference between discrete and continuous, again, the example that I often use in class is something that's discrete might be something like shoe sizes. So there's certain discrete values that are used for shoe sizes, and you can imagine if you looked at the entire population, you'd end up with a histogram because we don't have in-between sizes. We have 5, 5.5, 6, 6.5, 7, 7.5, and so on up to, I don't know, like size 13 or 15. On the other hand, something like the length of someone's foot, the length of your foot, that is something that's going to be probably continuous. And it's something that's actually approximately normally distributed. And these numbers are actually in inches. So because of the way that we do these things, we make shoe sizes in certain discrete sizes, but the length of your foot could be any number in a reasonable interval of numbers. So go ahead and pause the video here and complete the rest of this page. Classify each variable as discrete or continuous, and click play when you've done all that. All right, so hopefully you've gone ahead and tried to classify each of these variables as they're either a discrete numerical variable or a continuous numerical variable. Most of these are pretty straightforward. The first 7 of these are pretty straightforward, either discrete or continuous. So something that's counted generally is discrete. Something that is measured generally is continuous. So again, this is not a hard and fast rule, but generally things that are counted tend to be discrete. Things that are measured tend to be continuous. The last 3 on here are a little bit ambiguous. You could argue them either way. It kind of depends on how you end up rounding. If you say miles driven by Fairfax County school bus drivers, like rounded to the nearest mile, then yeah, it's probably going to be a discrete number. That's different from if you said the distance that Fairfax County school bus drivers go each day. And the same is true for number 8 and number 9 as well. If you're having trouble with the discrete and continuous part, most of you guys probably won't, but please make sure to ask me about this next class. It's not the biggest deal except for the next part, which is when it's going to become really important. The next example that's on the following page is about hockey games. So in the 2010 season, there were a whole bunch of games that were played by the NHL, and this right here is going to be a probability distribution. We're defining the random variable x to be the number of goals scored by a randomly selected team in a randomly selected game. So here we have a probability distribution. And go ahead and put these into your calculator. You can pause the video if you need to, and put these numbers into your L1 and your L2 in the calculator, and you'll see why in just a minute. Also, you should already be able to do part A. So go ahead and pause the video and show that the probability distribution is legitimate. Hopefully you remember that the way you show that a probability distribution is legitimate has 2 parts. First of all of the probabilities need to add up to 1. That's the part that usually people remember, but don't forget you also need to have that each of the probabilities needs to be between 0 and 1. Since both of those things are true here, all the probabilities are between 0 and 1, and all the probabilities add up to 1. This is a legitimate probability distribution. Now, for part B, I've already given you a picture of the histogram, but just to remind you how this works, If you are to look on your calculator, and now hopefully you have these numbers into your calculator, the way you do a histogram is you go stat plot, so second y equals, and I'm going to choose to create a histogram using my values that I have in L1. Also, for the frequency list, this is the heights of the bars. Generally, we leave this at 1 and just let the numbers in L1 do that. I'm going to use the numbers in my L2 as the heights of my bars. Now, let's go ahead and take a look at what this would be. If I go to, if I just look at a standard zoom, I probably would not see very much because those numbers are quite small. What I want to do is I want to set my window so I can actually see these things. Now, if you look on the actual table of the values that you have, we don't have any x values that are less than 0. So let's set our x from 0 to 10. I want the bars to have width of 1. Negative y values in this case don't have any meaning, so I'll set that at 0 as well. And the largest probability here is like 0.229. So if I say like, okay, like 0.24 or 0.25, that should be plenty tall enough for this. Now if I hit graph, I should be able to see that histogram. Don't forget, if you hit trace, you can see what each of the values of the bars are. For instance, this bar represents values between 0 and 1 and has a height of 0.061, and I can scroll over and see what the heights of each of these bars are if I need to. So you should see a histogram that's similar to the one that's on your paper. If you look at the one that's on the paper, you should see something like this. Go ahead and pause the video and describe what you see. Okay, hopefully you remembered that when you see describe a distribution, what we're talking about is SOCS. So hopefully you said something like the distribution is skewed right, maybe with the most likely number of goals being 2 or 3. All the values are between 0 and 9, but it's pretty unlikely to get more than 6 goals in a game, or something like that. If you did a more bullet point type of thing, don't forget you have to address all 3 things, shape, center, and spread. I mean, in this case, I don't really see any outliers, so other than saying there probably aren't any, you probably don't need to address that too much. If you mention that this shape is skewed right, your center is, if you give a mode or a median or a mean, something like that, that would be okay. The spread, all values are between 0 and 9 goals. So, Part C, what is the probability the number of goals scored by a randomly selected team in a randomly selected game is at least 6? And what's the probability that it's more than 6? Please note, for this example, these two things are not the same, and this is actually going to be an important thing. So at least 6 means 6 or greater. More than 6 does not include the value 6. So don't forget, these are different things. Go ahead and pause the video and see if you can come up with both those probabilities. So finding the probability that x is going to be at least 6 is the probability that you're going to get x greater than or equal to 6, which is going to be the probabilities of 6, 7, 8, and 9 added up together. So we're going to show some work here, and I'm going to say that's going to equal 0.061. For the second part there, the probability that x is greater than 6, the number of goals is going to be more than 6. That's not going to include the probability that x equals 6. It's instead just going to be the probabilities of having 7, 8, or 9. So I should get a smaller number than for the first one. Please note the fact that these numbers are different is one of the things that's true for these discrete random variables. All right. So that's the first thing, is talking about how to use a probability distribution to find probabilities. Let's talk now about mean and standard deviation. So if x is a discrete random variable with some probability distribution, so here we have x1, x2, x3, these are different values of your variable, and the probabilities are the ones that go with those. So for instance, P1 is a probability of getting the value x1, P2 is a probability for x2. Then to find the mean, and here we're introducing some new vocabulary, the mean is also known as the expected value of x. We're going to multiply each value by its probability and add the products. So in order to find the mean, which is also known as the expected value, which has this notation, the expected value of x, I would take x1, multiply by p1, and then add that to x2 multiplied by p2, and add that to x3 multiplied by p3. And if I were feeling like I didn't want to write out all these terms, because of course I could, but if I wanted to write it in a more compact form, we can use sigma notation. So I'm going to add up for each value times its probability and add up all those values. So, a couple things about the mean. The mean is a long-run average outcome we'd expect after many, many trials. So, again, it's the long-run average outcome we would expect after many, many trials. And again, don't forget that we can say mean or expected value. Those are equivalent terms here. The expected value does not have to equal one of the values in your distribution. So you do not need to round this. Again, it's an average. That's a mistake that a lot of people make. All right, I think that's long enough for the first half of this video. Make sure that you've caught up to here, and then join me over in part 2.